The first thing we're going to talk about today is the difference between exponential growth and decay. And we're going to draw a quick little picture of what exponential growth looks like and what exponential decay looks like. It might help if my coordinate planes were decent looking. So exponential growth, it's when you have a very, very small number of something and then it gets exponentially bigger. So on the left side, it approaches a horizontal asymptote. On the right side, it gets exponentially larger. Exponential decay is the opposite. You start with a whole bunch of something and it gets smaller and smaller and smaller, eventually approaching an asymptote at 0. Exponential growth occurs when your b value is larger than a whole. So if your b value, remember this is y equals a times b to the x. So we're looking at the number that's raised to the exponent. If the number raised to the exponent, the b value, is bigger than a whole, bigger than 1, it's exponential growth. If that b value is between 0 and 1, that means less than a whole, like 1/3 or 1/2 or 0.2 or something like that. So if your b value is less than a whole, then you have an exponential decay situation. So there's 4 equations shown here. We need to decide if these are exponential growth or exponential decay. So each time we're going to look at the b value. So in number 1, is that b value of 2/3, is that bigger than a whole or less than a whole? Less than a whole. 2/3 is not 1 whole. This is exponential decay. In the next one, it says 3/2. That b value is 3/2. Is 3/2 less than a whole or more than a whole? Which means this is exponential growth. Number 3 and number 4 are tricky. Number 3 appears to be growth. I see that the b value is 3. But I also see that in the exponent there's a negative. And a negative number in the exponent, a negative in front of the exponent, indicates a horizontal reflection, or reflection over the y-axis. So if we take this exponential growth function that I just accidentally highlighted in green and reflect it over the y-axis, what will that start to look like? Decay. If you take this growth graph and reflect it horizontally, now it suddenly is decay. So this one, even though it looks like growth because of the 3, because of the negative in front of the x, that flips it around and turns it into a decay function. Number 4, same kind of thing. It appears to be exponential decay because 5/9 is smaller than a whole. So you've got this decay graph, but then the negative flips that decay graph over the y-axis, making it look like a growth graph. So this one is exponential growth. I will not give you problems like 3 and 4 on a test or a quiz because I think that's cruel. It could maybe be a bonus question. So if you know what you should know about that b factor and what the negative in the exponent does, you should be able to get that answer really quickly, but that's not a question that I would put for points. Okay, the growth model and the decay model. This is things like population growth. They use a growth model for population growth. The value of a car. If you buy a 2017 Chevy Malibu, is it going to be worth the full purchase price 10 years from now? No, it's going to massively decrease in value. The only types of cars that increase in value are like the super amazing, super crappily old classic cars. Not crappily old, but, you know, the classics, like the really, really old cars. So the growth model and the decay model. I want you to look at these 2 models that are highlighted. Do you notice that these 2 models are exactly the same except for one thing? The growth model has a plus The decay model has a minus. Basically, you're taking one whole plus the growth rate. For the decay model, you're taking a whole minus the decay rate. So that's what's going to make that number that's raised to the exponent either be bigger than a whole or less than a whole. In here, the a value, and it's not written in here, so you should write it in here. The a value represents the initial value. So the initial price of the car, the initial population, whatever the starting value is, that's your A. And then it tells you in here that R is the growth rate. So number 4, the value of a car in thousands of dollars, and that's kind of a key phrase, can be approximated by the model y equals 31 times 0.92 raised to the t, where t is the number of years since the car was new. Couple of things that you need to know. 31 is the initial value. Was it $31 or $31,000? So keep in mind here that 31 means 31,000. First, tell whether the model represents exponential growth or exponential decay. Look at the number in the parentheses. Is it bigger than a whole or less than a whole? Less than a whole, and that indicates that it is exponential decay. Identify the annual percent increase or decrease in the value of the car. This is the tricky problem that the EOC, the ACT, or a test might try to confuse you on. The number inside the parentheses is 0.92. So I'm going to write down 0.92. Where did that 0.92 come from according to the original exponential decay formula? Inside the parentheses, what do you see? 1 minus r. That 0.92 came from doing 1 minus r. This question is asking us, what is r? So you have to solve that equation. So if you subtracted 1 from both sides of that equation, you'd end up with negative 0.08 equals negative r, so r equals 0.8 or 0.08, which means 8%. Think of it as percentages. If you're keeping 92% of the value of the car, that's what this equation says. This equation says we're starting with $31,000. We're keeping 92% of the value of the car each year. So what percent of the car's value are you losing each year? 8%. So think about, in that 0.92, what would it take to get back to a whole? It would take 8% to get back to a whole. So the annual percent increase or decrease, the annual percent decrease is 8%. Okay, I don't like problems like C, but we have to do them. Estimate when the value of the car will be 9,600. The first thing you need to think about in C is, because this model uses 31 in place of 31,000, think about what would 9,600 be? It would be 9.6. 9,000 would be 9. And then that 600 would be 0.6. So since we've kind of altered the format of the numbers, we have to think about that with that 9,600. So 9,600 is 9.6. Estimate when this model will give us an answer 9.6. Basically, you have to grab your calculator and you have to try a certain number of years until you get 9.6 as your answer. So in your calculator, the model is 31 times 0.92 raised to the number of years since the car was new. How many years should we start with? What should we try? Let's try something nice and even and round, like 10. You guys want to try 10? Okay, after 10 years, according to this model, the car is going to be worth 13,000. So that's not enough years. We want more years. So I'm not going to go quite to 20. I'm going to try 15. See what happens when I try 15. After 15 years, the car has a value of $8,875. That's too much. So now we have to kind of find the difference between 10 and 15. So what number should we try next? Should we try 14? Ooh, we tried 14. We got 9.6. That'd be 9,646. So after about 14 years. Now, after we learn about logarithms in the second half of this chapter, we could actually solve this equation and figure out exactly how many years. But right now, we don't know how to do that because we haven't done logs yet. Number 5, the population in thousands of Austin, Texas during a recent decade can be approximated by y equals 494.29 times 1.03 raised to the t. So this 494.29 means 494,290. First, does this model represent exponential growth or decay? Why does it represent growth? The stuff being raised to the exponent, the b value, is bigger than a whole, so it's exponential growth. Identify the annual percent increase or decrease. They want to know what is r. Well, where did 1.03 come from? 1.03 came from doing 1 plus r. Why is it 1 plus r this time? Because it's growth. So solve that equation and you would get 0.03 equals r, so that would be 3%. Estimate when the population was about 590,000. Now 590,000, that means we're looking for a value of 590. So try in your calculators. Try plugging in, I don't know, 5 years, 10 years, whatever you want to try, until you find how many years it will take to get to about 590. When we try 5, we get not a large enough number. We try 10, it's too big of a number. So if we try something like 6, is it 6? About 6 years. These problems were designed to get you familiar with all the pieces of those exponential growth and decay models. When we turn the page, we are actually going to create the growth and decay models ourselves.